Hi folks, and welcome to the fourth lecture of the Experimental Design and Analysis series for the Core Skills modules. This lecture is about statistical probability, which sounds a bit evil, but it's actually a fairly straightforward idea, and it's right at the heart of most of the analysis that we do across the life sciences. When we've got data and we want to make inferences from those data, this is a really critical idea. So in short, if you were going to learn only one thing from all my lectures, it's this particular thing, the idea of statistical probability, and in particular a thing called the p-value. Okay, so I'm going to look at this idea, this concept, in the context of the sorts of differences that we look for in data sets, as opposed to trends, which we're going to deal with later on in the course. So for the next few weeks, I'm going to be talking about differences on and off. Hence the slide here, which is to remind me that we're talking about differences. What we've got here actually is two seemingly nearly identical butterflies. In fact, these are totally different species, one of which, the monarch, was traditionally thought to be venomous, or not venomous, sorry, noxious, so unpleasant or poisonous to eat. And the other, the viceroy, was thought to be a harmless mimic. Turns out the story's a bit more complicated than that, but this is illustrating the concept of mimicry, which is something that I study myself. It's one of my main research interests, is how and why evolution has given rise to patterns like this. But that's for another day. It's merely to remind me that we're talking about differences. Okay, so the outline for today's lecture, which again is going to be in three parts, is first of all to look at the scientific process, the scientific method that we described in the first lecture, and focus in on the next step in that process, having talked about setting up a good hypothesis, and then talked about how we set up a good study design to collect the data. We're now ready in this method, in this scientific process, to try to make inferences from the data. And that will involve us talking about statistical probability and the idea of statistical significance. So that's a big job for today, is to look at that, and a major learning outcome for the course is that you understand and are able to define a p-value. Then we're going to look at these ideas in the context of looking for biological differences in systems that we might be interested in. And that's going to bring us to the idea of a simple statistical test called the t-test, which is really going to give us a nice example of how the concepts of statistical probability work when we employ them in actual analysis. So it will be another learning outcome for the lecturers, that you understand how the t-test works and what it's for. So in the first part then, we're just going to focus in on this concept of statistical probability and try and hammer home what it means, because it's really important in the context of the scientific method. So to remind you, here's that scientific method written out in a sort of linear cartoon style form, and we're homing in now on near the end of this process the idea that we've got some data from an experiment or a set of observations, and we now want to know whether or not we should reject the null hypothesis and try to formulate a new hypothesis, or whether we found support for our null hypothesis. So if you remember, this is a kind of potentially destructive component of the scientific method, where we essentially throw data at hypotheses in the hope that we find evidence that the hypotheses are false, in order that we can falsify them and then move on to be creative and create new ideas or new hypotheses. It's a rather negative, conservative view of science, but it rests on this idea that we can use data to make inferences about hypotheses, and that's what this lecture is all about, really. So the question is, how do we evaluate the data that we've collected, or rather, how do we evaluate the hypothesis using the data we've collected? And the answer, broadly speaking, across all of the life sciences, is going to be statistics. And so while as biologists you probably didn't sign up to learn about stats, some understanding of how stats works, without necessarily getting too bogged down in the underlying maths, is a really important part of being a scientist. And you know, this is painfully obvious when you look at science in the media. I mean, take the COVID crisis at the moment. Scientists are busy trying to make inferences from the data they're collecting in real time, you know, in a situation of global emergency. and they're trying to feed politicians sensible inferences from those data so that politicians can then make decisions which might save people's lives. And those inferences are in many cases centred on looking at data from the burgeoning pandemic and trying to work out whether the data are consistent with a hypothesis the scientists might have about what's going to happen next, or about what the cause of the spread of the disease is. So having a systematic and objective mechanism for making that judgment is absolutely central to the idea of modern science. And that's what we're going to do today. So when you use a statistical test, it calculates the probability of the data that you've observed given the null hypothesis. This is a kind of critical concept that lies at the centre of statistical testing. We're calculating the probability of the data if the null hypothesis is true. So when I say given the null hypothesis, that's what I mean. If the null hypothesis is true, what are the chances that I would have seen the data that I've seen? So we can start thinking about this in really simple terms. Ordinarily, actually, I would do a kind of interactive thing with the class in the lecture theatre, and we'll have some chance to do interactive stuff in the wrap-up sessions that are running live later in semester. But for the time being, I'm just going to imagine, I'm going to do a kind of thought experiment here in the recording. So let's stick with COVID, since it's at the front of everybody's mind, and something else that's always at the front of my mind, which is chocolate. So I'm a massive chocolate fan. And I was looking at the COVID stats for the rate of deaths in different countries and thinking, that's a bit weird. Some countries, or many countries which are good at producing chocolate, seem to be have particularly high death rates from COVID, which is obviously a major concern to me. I would never want there to be an association between my favourite thing in the world, chocolate, and one of my least favourite things in the world, the coronavirus. So I thought, well, let's actually have a look at some of the data. So I sampled 3 countries which are well known for producing excellent chocolate: Belgium, Switzerland and Ecuador. And then I sampled 3 countries which, in my experience, produce rubbish chocolate. No offence if anybody's from Australia, India or the US here, but when I've had chocolate in those 3 countries, I have found it wanting, sadly. So I thought, let's look at the death rates in those countries and see if there's any difference. So it turns out, if you know anything about the death rates in different countries owing to COVID, you'll know that Belgium is one of the worst in the world. Belgium suffered really badly, and you can try to put that down to all kinds of different possible reasons. That's not the job here for us today, but the death rate per million people is over 1,000 in Belgium. So 1 in 1,000 people in Belgium has died of COVID, which is a pretty shocking statistic. Switzerland has a reasonably high death rate, and Ecuador has a very high death rate, not quite as high as Belgium, but also pretty high. So on average, the 3 countries that I picked, which are chocolate producers, have a death rate of 691 people per million. The 3 countries I picked, which are representative of countries that don't produce good chocolate, Australia, India and the US, well, Australia and India have very low death rates per capita for very different reasons, I suspect. But again, we won't get into that. The US, on the other hand, does have quite a high death rate, amongst the highest in the world. But the average death rate for those 3 countries is 283 deaths per million. So we look at these numbers and we think, wow, okay, 691, 283. So countries that produce chocolate, good chocolate, seem to have a death rate which is nearly 3 times as high as countries that don't. So should we report to the government or the World Health Organization that there's an association here that we need to investigate? Maybe something about making good chocolate makes you prone to COVID or something. Or should we take a step back and think whether the pattern that we see on screen is real or not? Is it telling us anything meaningful? Or in fact, are we looking at the results of random chance? So you can see, just look at the non-chocolate producing countries. There's huge variation among countries in death rate. Is that variation primarily or even significantly determined by chocolate production or associated with chocolate production? Or are we just looking at random variation, and it just so happens that the 3 countries I chose who are good at producing chocolate have a high death rate on average? And really that's the sort of question that lies at the heart of most scientific inferences. When you're trying to make inference from data, this is exactly the sort of problem you're faced with. You've got some data, they show a pattern, The question is that pattern real? Does it represent an underlying biological reality, scientific reality, or is it the result of random chance, given that data points will vary randomly? In this case, death rates vary from country to country for a whole load of reasons which have nothing to do with chocolate. So that's essentially the problem, and we're now going to look at the solution, how we actually quantify the probability of getting data like we've seen if the null hypothesis is true. So if you remember, the null hypothesis says that there's nothing happening. In our case of the chocolate example, there is no difference in reality in the death rates of countries with which are capable of producing good chocolate and those that are not. And we want to know, well, what are the chances of seeing that difference in mean death rate that we saw by chance if it is fundamentally true that there is no real association between COVID death rates and chocolate consumption. So we can describe this in many different ways, but essentially we're trying to quantify the probability of getting results like ours given the null hypothesis. And we're going to use a statistical test to calculate that probability for us. And the probability that we're talking about is very often referred to or abbreviated to just simply p, or a p-value. So you will see in textbooks and scientific papers and lectures from now until the end of your degree very often this thing called p cropping up. And it is your job as a scientist to understand what p means, because if you don't, then you can't really make sense of any science that you read, which involves data, and that's most science. So you're going to see p-values a lot. They mean the probability of the data under the null hypothesis, and we're going to explore exactly what that means with some other examples. And in the case of our chocolate example, we're not going to look at that one anymore, but the point is we're looking for whether the difference in the two groups of data points we've got is something that could easily have arisen by chance if the null hypothesis is true. Okay, so how do we calculate p? We're going to look at a really simple example using sperm. So we're going back to an example I raised in an earlier lecture, and you'll see by the end of this lecture we actually get to the whole point of this sperm swimming speed example, because there's an interesting experiment I want to look at. But for the time being, we're just going to ask a question about a single sperm, in fact. Let's imagine we are looking at a sample of sperm. Maybe we're in a fertility clinic and we're trying to assess the fertility of a patient. Now we see an unusual looking sperm, and we want to know, is this sperm a normal healthy sperm or not? So in the case of this study, what we're going to do is we're going to calculate the swimming speed of the sperm as our measurement of whether the sperm might be normal or not. And we're going to compare the data we get, the sperm swimming speed, with what we expect from a healthy normal population. So we're going to make the assumption that healthy normal sperm swimming speeds are normally distributed with a mean of mu and a standard deviation of sigma. So what we're doing here is very common in statistical testing. We're going to assume a particular distribution. We're going to assume that the underlying population is normal. And once we've made that assumption, that's going to allow us mathematically to calculate p. It is a big assumption. It is not always correct, as we've already seen. But as long as you're aware that you've made that assumption, then you can interpret p appropriately. So we measure the speed of the individual sperm, and then we ask, what is the probability of us seeing that particular speed of swimming, a sperm that swims either that fast or that slow, if the null hypothesis is true? And the null hypothesis obviously is something that you're in charge of as a scientist. In this case, our null hypothesis is that our individual sperm's swimming speed is not significantly different from that of a typical sperm. So we're saying there's no difference between our sperm and a typical sperm. What's the probability of seeing the swimming speed we've recorded then? So we answer that question making use of the normal distribution in this particular example, because we've assumed an underlying normal distribution. And if you remember, the normal distribution has some really predictable properties. You can write it down as an equation if you want to, and it has known mathematical properties which allow us to calculate a probability p, given the assumption that there is a normal distribution. And the key properties we're making use of is this idea that 95% of the data in a normal population lie within 1.96 standard deviations of the mean mu. So if you are able to assume that, then you can immediately start to say something about an individual measurement that you've made, which you think may or may not be from this underlying population. So let's say we measure our sperm, our individual sperm, and we find that it's swimming very slowly. If it's swimming so slowly that its swimming speed is less than 1.96 more than 1.96 standard deviations away from the mean of the population with which we're comparing it, then what we're saying is the chances of observing that sperm, if we drew a sperm at random from the underlying population, the chances of observing a sperm with such extreme swimming speed is less than 5%, because a sperm with a very slow or a very fast swimming speed lies outside the 95% region of this normal population. So a sperm that is that unusual is going to crop up less than 5% of the time if we pick a sperm at random from the population. So as long as we know what the background population is like in this example, we can take an individual measurement and we can say how likely is it that we would get that measurement given that it comes from the normal population that we're comparing it with. Because the null hypothesis says it does. The alternative hypothesis would be there's something odd about this sperm. It doesn't belong to the population of healthy sperm with which we're comparing it. For example, it might be damaged, unhealthy, belong to a different individual, who knows. On the other hand, if we'd measured the swimming speed and found, okay, it's somewhat slower than average for the population, but it's not outside this 95% region, then we would conclude that the probability of seeing that sperm swimming speed is, under the null hypothesis, is greater than 5%. So you very often see in statistics this 5% cutoff used to distinguish between events which are quite likely under the null hypothesis, like this one illustrated on screen, and events like these, which are very unlikely under the null hypothesis, so unlikely that we might regard them to be, that we might be willing to ignore them and conclude that the null hypothesis does not actually apply in this case. So this is the process. We are effectively here calculating p. Now, we looked at it kind of graphically there and asked whether p was greater or less than 5%. But we can actually, using a computer, calculate p precisely. So you'll see p values like 0.323 quoted, meaning there's a 23.2% chance of observing the data if the null hypothesis is true. So what we did with our example is we compared some data, in our case just a single sperm swimming speed, with a hypothetical population that had a known distribution. And that allowed us to calculate p. And that's how all statistical tests work. They take a known hypothetical population and they compare it with either one or more data, and we ask how likely are the data to have cropped up in a world in which that hypothetical population is really true. So that's how they work, or I say not all statistical tests, but most statistical tests that you're going to encounter work on this basis. And because data sets are often quite complicated, and the sets of assumptions that you might have made, in our case we assumed a normal distribution, can be quite complicated, there is a general process here by which we calculate something called a test statistic from the data, and then ask how likely that is under the assumption of the normal distribution, and that allows us to calculate the p-value. As opposed to my very simple example where we just had a single data point. So I'm imagine we've got lots of data, we would normally calculate a statistic from those data, which we compare with an expected distribution which has known mathematical properties, and from that we calculate p. So we're going to see lots of examples of that as we go through. In my example, it's so simple that we're able to simply look at the data point itself and compare it with the distribution. Okay, that's the end of the first part of this lecture. So far, in some senses, relatively abstract. I mean, I've tried to illustrate with examples the concepts that I'm talking about, but we're going to come back to the same concepts now after the break in the context of testing for differences in biological data sets, where we'll see the same idea coming up again, and hopefully by the time we get to the end of the lecture it will have sunk in what I mean.